Session 10, Unicode and Encoding in Python. Agenda of the session is bits and bytes, hexadecimal numbers, encoding. Bits and bytes. A bit is a signal that has only two possible states. There are different ways to symbolically represent to representing a bit that means all the same thing. For example, you can represent 0 or 1, yes or no, true or false, on or off. Computer understand only this language because we have magnetic spots which can be polarized, non-polarized. We have surface which can emit some light, which can absorb the light. We have electrical switch, we have electrical flip-flops which can store 0 or 1. So what we have essentially is only these two states. Because computer is an electronic device, electricity and electronics, so these are represented by means of electricity and electronics part only. ASCII, American Standard Code for Information Interchange, uses what you and I would just call numbers like 0 through 127, more precisely called numbers in base 10, that is a decimal number system. You can also express each of these base 10 numbers with sequence of bits, that is 0 and 1 only. Like if it is decimal 0, you can represent it as binary 0, this is compact form, but in binary padded form. Why this padded? Because we use this number of digits. There are total 8 bits which are used to represent this number. So 8 bits means 1 byte. So this 1 byte is fully capable of representing 256 characters, but ASCII uses 7 bits only. Essentially, you will see that because they use up to 127, 0 to 127. So 1, if you read in binary format, it is 1, 2, it is 10, 11, 100, 101, 110, 111, 1000, 1001, 101. The pattern is quite simple to find out. This is alternatively changing 0, 1, 0, 1, 0, 1 and same way. Every alternate this is changing. The second digit is changing after every 2 cycles. So here it is 0, 0, you can say that way, and here it is 1, 1. Similarly, next 0, 0, then 1, 1, 0, 0, 1, 1. So, and next will change at 4. If you understand that carefully, very easily, 1 second. Next will be you changing at every 4. That means here it is changing 0, 0, 0, 4 times 0, and then it is 4 times 1, then 4 times 0, then 4 times 1, and so on and so forth. Next time it will be 8 times, 8, 0, 8, 1. If you look at this pattern, this is same thing. Twice 0, 0, 1, 1, 0, 0, 1, 1. I am talking about the second digit. Third, 4 times. 0, 0, 0, 0, 4 times 1, 4 times 0. Next will be 8 times 0, 8 times 1. So if you continue like that, you can easily convert any decimal number into binary equivalent very easily. And computer understand this form. Computer take a minimum 7 bits or 8 bits depending on the character set being used to represent the numbers and the alphabets. This binary form is full and sufficient enough to represent all the characters. ASCII string as sequence of bits in Python. Each character from the ASCII string gets pseudo encoded into 8 bits, that is 1 byte, with spaces in between. The 8-bit sequence that each represent a single character. This is a function available that is introduced in Python 3.7. I don't have it right now because I am using Python 3.6. But if you use Python 3.7, I verified that yes, if you use is ASCII will give you you know corresponding equivalent of any character, any digit, anything in a binary format. Look at this example. This is function we are defining make bit sequence. You pass s as a string, and then if not is ASCII value is ASCII value only allowed, and if it is ASCII then display this is use this function join f ordi 08b for I in s. This is a loop part. Now if you understand this is we are calling join, we are using this ord function, passing the value I, counting from 0 to 1, that is I, from I in s means if it is number I in s. So first is ASCII function is being used here. So make bit sequence BITS. So this is BITS. Similarly CAPS, CAPS. Then this $25.43, and this is binary equivalent of this. So if you carefully look at all these string, whatever they are passed, they are ASCII characters, ASCII alphabets or ASCII digits. They are converted to equivalent ASCII code. So this is the binary representation of these numbers, just for you understanding. So this function is available in 3.7. In 3.6 we have other functions to help us with this. For example, this function ORD is available in Python 3.6 also. Need more bits. This critically important formula that's related to the definition of a bit. Given a number of bits n, this is n, the number of distinct possible values that can be represented in n bits is 2 raised to the power n. This 2 is the base, that means how many digits taken at a time. So if you take 2 digits at a time and you use 3 bits, I mean total 2 digits possible, base is 2, and you take 3 digits at a time. So how many possible values are there? This formula will give you 2 raised to the power 3 is equal to 8, and it will give you 8 possible values. If you have 4 digits or 4 bits and total number of digits are 2 only, then you can have 16 possible values. If you take 2 raised to the power 8, and that will be possible values will be, that is 2 raised to the power 8, 64. This formula goes on and on and on. So therefore this is the formula. If you take for example, if you take base is 10 and you take 2 at a time, so that will give you these many possible values. So that is base number of digits at a time will be the formula, and this formula is written as a function, and this is a function I defined. Same function, define possible values, number of bits, integer type, return integer value, return 2 multiplied by that is raised to the power number of bits. So when I tried this formula, tried this function, calling this function, number of bits is 8, I want to take 8, possible values will be 256. I was wrong, 2 raised to the power 8 is equal to 256. I missed that in the previous. 2 raised to the power 8 is 256. So therefore if we take 1 bit at a time, that will give you 2 raised to the power 1, that is 2 possible values. 8 bits, 2 raised to the power 8, 256. 64 bits will give you 2 raised to the power 64, and these are the possible values. Fortunately, unfortunately, this formula works everywhere. If you use Excel, if you have used old Excel in your old days, you will recollect that their total possible number of rows were 64,536. 64,000 or 32,000 columns. That number is, all these numbers are coming from these possible values, these possible digits, that how many digits are being used to represent that number. That number of digits being used gives you total actual values. That is the reason sometimes you will find the limit, highest limit at 32,768 or 32,767. That value come from 2 raised to power 16. If you take out one bit for sign, you are left with 15 bits. 16 minus 1, 15 bits, because if you are using signed values, signed numbers, you are leaving one bit for the sign. So bit left for the actual number is 15, and 2 raised to power 15 is nothing but 32,768. 32,768. If you start counting from 0, then you have to take this one number less, because total possible combinations are these many. So if these were the possible combinations, so what will be the one value less than this? Because we are starting from 0, so highest number will be 32,767. If you take it negative side start with minus 1, so the value will be 32,768 only, minus sign. Because minus sign, minus 1 never start with minus 0, so it starts with minus 1. So we have actual total possible values 32,768. So this is all representation of this. ASCII is, strictly speaking, is a 7-bit code, not even 8 bits. The ASCII table contains 128 code points and characters 0 through 127. Same, 0 through 127. So that means we are using total 128 possible values. Now what is this value? That if you calculate, this is 2 raised to power 7, that makes it to 128. So that is the reason ASCII is using 7 bits only. The issue with this is that modern computers don't store much of anything in 7-bit slots. They traffic in units of 8 bits, conveniently known as byte. So 8 bits together form 1 byte. So group of 8 bits is used to represent a single character properly. Now decimal to binary. You can express the number 0 through 3 with just 2 bits. Why? Because you can start with 0, 0, 0. Like if you are using 2 bits, so you can have 0, 0, 0, 1, 1, 0, 1, 1. So if these are binary numbers, the corresponding equivalents are 0, 1, 2 and 3. So you have 4 possible values, 0, 0 through 1, 1. Or you can use 8 bits to express them. You just have to use padding, add padding zeros, leading zeros. The highest ASCII code prints 127, requires only 7 significant bits, as I explained just now. There are other number systems. In addition to decimal, the alternatives include the following common number systems: binary, that is base 2, octal, that use base 8, hexadecimal, that use base 16. The base 16 or base 8 actually means how many digits you are taken at a time. So the hexadecimal number system takes 16 bits at a time, and these are 16 digits are 0 to 9 and then A to F. These are 16 possible symbols which represent hexadecimal number system, and they can be easily converted to equivalent binary. If you start counting, because base 16, to reach to this base 16, we need just 4 digits. So that means if you start using 0, 0, 0 4 times and you continue writing it, you will end value will be, last value will be 1, 1, 1, 1, and that is the F value. So 16 total digits in binary is very easily convertible from using 4 bits of binary. But what does it mean for us to say that in a certain number system, numbers are represented in base n, base 2, base 8, base 16? What is the meaning of that? What is the significance of this? We need to understand number system a little with examples. One way to demonstrate how different number system interpret the same thing is with Python's integer constructor. If you pass a string to integer, Python will assume by default that the string expresses a number in base 10 unless you tell it otherwise. So for example, if you say integer 11, you will see the output 11. I verified that in 3.6 version, it works very well. This is a screenshot. If you pass 11 but optionally you pass base 10, which is nothing but which is default, so you will get the same value. But if you pass base 2, you will get 3, because 1 1 is nothing but 3. If you pass base 8, it is 9, that is octal number. And if you pass base 16, then it is 17 in octal number, hexadecimal number system. So base 10 means decimal, base 2 means binary, base 8 means octal, base 16 means hexadecimal number system. There is more common way of telling Python that your integer is typed in a base other than 10. Python accepts literal forms of each of the 3 alternative numbering systems. For example, type of literal, we don't need anything for normal integer. Yeah, if you are talking about binary literal, you can use 0b or 0 uppercase b, and so it will become 0b11. If you are taking octal literal, so you use O, small o or uppercase O, so 0o or 0 uppercase O. So 11 will be 0o, then 11. So B for binary, O for octal, X for hexadecimal with a leading 0. So 0B, 0O or 0X, they can be used to literally represent the corresponding binary, hexadecimal, decimal, or these, I mean binary, octal or hexadecimal number systems. Binary, octal and hexadecimal. Now this is a table which gives you all the numbers from 0 to 20. 0 to 16 is what we need actually, because we get hexadecimal if you are converting, then rest of the numbers will be easy to form. So if we start counting from 0 to 16, then their corresponding binaries are this. These are the corresponding binaries. 0 to 15, sorry, 0 to 15. So 0 to 15 makes you 16 total digits. So 15 is represented by 0B1111. If it is octal, 0017. If it is hexadecimal, is 0XF, because as I said from A to F, and 0 to 9. And the leading literal you can use, that is 0x. So here's how you could type the binary, octal and hexadecimal equivalents of decimal numbers 0 through 20 as an example. Any of these are perfectly valid in Python interpreter, shell or source code, and all work out to be type integer if you are talking about here this column. Now after understanding these bits and bytes, the basics of number system, let's understand how the character encoding works in Python. There are many character encodings in Python. The best way to start understanding what they are is to cover one of the simplest character encoding, that is ASCII. Whether you are self-taught or have a formal computer science background, chances are that you might have seen ASCII table once or twice somewhere. Entire ASCII table contains 128 characters. The table captures the complete character set that ASCII permits. It includes all these characters like lower English letters from A to Z, small a to small z. They are different for computer. Small k, small a, uppercase A are all different. Uppercase A to Z. Punctuation and symbols like dollar, exclamation mark, white space, this is actual space, as well as a new line, carriage return, horizontal tab, vertical tab, and few others. They are all separate symbols in ASCII. Remember that they are not same. Some non-printable characters such as a backspace that can't be printed literally in the way you can print letter A. So these symbols together, even the number which you write 0, 1, 2, 3, 4, 5 in ASCII, they are represented by the corresponding ASCII code. Formal definition of character encoding. At a very high level, you can say that it's a way of translating characters such as letters, punctuation symbols, white spaces and control characters to integers and ultimately to bits, because computer understands only bits. Each character can be encoded to a unique sequence of bits, and this sequence of bits is called character encoding. Character segmentation. The various categories outlined represent group of characters like 0 through 31. They use control or non-printable characters in your ASCII table. 32 to 64, they include punctuations, symbols, numbers, and space. 65 through 90, uppercase alphabet letters. 91 to 96, additional graphemes such as this square brackets and slash. 97 through 122, lowercase English alphabet letters. 123 to 126, additional characters or additional symbols like curly braces and vertical bars. 127 is control non-printable character delete key of your keyboard. So characters are segmented into different ranges. Each single character has a corresponding code point, which you can think of just as an integer. It's quite simple. You convert these numbers like 65. If I convert this 65 into binary, that will be uppercase A. 65 is the ASCII code, and the corresponding binary is actually being used inside the computer. So if I try to convert this into binary, whatever the binary equivalent of the 65 comes, that is nothing but uppercase A in computer. The string module. Python string module is convenient one-stop shop for string constants that falls in ASCII character set. Here's the code of the module. White space, these are all white space. This is blank space /t /n /r /v /f. Lowercase, all lowercase letters. Uppercase, ASCII letters. Digits, hex digits, octal digits, punctuations, and printables. That is digits plus ASCII letters plus punctuation plus white spaces. Very easily you can try this. Import string. What's wrong with ASCII? Now when you type this, are they ASCII characters? When you try R strip punctuation, so what we are doing is we are using a function strip punctuation marks from the character. So when you try printing it, it will display only the text part of it. That is what's wrong with ASCII, and not punctuation marks. Remove all of them. Strip means remove punctuation mark. Right side. R means from right side strip the punctuation marks and display the characters only. Unicode. Unicode fundamentally serves the same purpose as ASCII, but It just encompasses a way bigger set of code points. There are a handful of encodings that emerged chronologically between ASCII and Unicode, but they are not really worth mentioning just yet because Unicode and one of its encoding scheme UTF-8 has become so predominantly used in computer world. Think of Unicode as a massive version of ASCII table, one that has this 1 million possible code points. That's 0 through 1,114,111 or 0 through 17 raised to power 2 raised to power 16. 17 multiplied by 2 raised to power 16 minus 1, or in a hexadecimal 10 F hexadecimal. In fact, ASCII is perfect subset of Unicode. The first 128 characters in Unicode table corresponds precisely to the ASCII character set that you have reasonably expect them to, and then comes the rest of the characters. Being technically exact, Unicode itself is not an encoding. Rather, Unicode is implemented by different character encodings. Unicode is better thought of as a map, something like a dictionary or a 2-column database table. It maps characters like A or this character or even this to distinct positive integers. A character encoding needs to offer a bit more. Encoding and decoding in Python 3. Python 3's string type is meant to represent human-readable text and can contain any Unicode character. The bytes type conversely represents binary data or sequences of raw bytes that do not intrinsically have an encoding attached to it. Encoding and decoding is process of going from one to another. Like if you have to decode UTF-8, then if you try to print it into you will get this CIAO, different sounds. Similarly, if you convert encode it to UTF-8, you will get this. So decode it. So this is encoding decoding functions. You can use encode and decode, and that I'll show you with a screenshot because I use this. In encode and decode, the encoding parameter is UTF-8 by default, though it is generally safer and more unambiguous to specify it. For example, resume, encode it to UTF-8 and you will get this answer. This is the UTF-8 representation of this. Similarly, encode this to UTF-8, you will get this, and do a reverse process of decoding, give the same value. For example, this one, you try the same but decode it in UTF-8, you will get the same resume. Similarly, decode this second one, decode it, and you will get this. So this is what I verified in 3.6. This is working fine. So encoding, decoding, whatever text you have. For example, this is the text I have. I try to encode it in UTF-8. I got the right answer. Resume, I try to encode it in UTF-8. I got the right answer. I try to decode them and I got the same equivalent encoded string. The results of str.encode is a byte object. Both byte literals like this and the second one, they represent the bytes of permit only the ASCII characters. This is why when calling El Nino encode UTF-8, the ASCII compatible EL is allowed to be represented as it is, but N with the tilde symbol is escaped to this character. That messy looking sequence represents 2 bytes. First is this and second is this in a hexadecimal. If you try to use join function, pass on the same value, these 2 bytes which you are talking about, this is the hexadecimal representation in the binary format. These are the hexadecimal digits and you are converting them to binary, and this gives you the binary representation of this. Built-in functions. Python has a group of built-in functions that relate in some way to numbering systems and character encoding, like ASCII is a function available in Python, bin, bytes, character, hexadecimal, hex, int, oct, ord, and str. You need to be well versed with these functions. You need to practice these functions in order to have better understanding, because they will be coming in the programs, in the project, in the sample programs which we are going to discuss. These can be logically grouped together based on their purpose, like ASCII, bin, hex, and oct are for obtaining a different representation of an input. Each one produces a string. The first ASCII produces an ASCII only representation of an object with non-ASCII character escaped. The remaining 3 give binary, hexadecimal, and octal representation of an integer respectively. These are only representation, not fundamental change in the input. Bytes, string, and integer. They are class constructors for their respective types, that is byte, string, and integer. They each offer way of coercing the input into desired type. For instance, as you saw earlier, while integer 11.0 is probably more common, you might also see integer 11 base 16. ORD and character functions are inverses of each other in that the Python ORD function converts a string character to its base 10 code point, while character does the opposite. So these are Python's built-in functions, bits and bytes, character encoding. That's all for this session. Thank you very much.